All right, so we're going to get into frequency response now. We've talked about these transfer functions, how to obtain them, what they are, and now we are going to move into frequency response, which basically what is frequency response is kind of the first topic here. But before I even talk about what is frequency response, I kind of just want to recap what we did in the previous module, which was we had some kind of a sinusoidal source. We'd have, let's just give myself a little RC circuit here, resistor and a capacitor. And again, let's just say I'm interested in the output voltage here, V out of t. Let's call this V in of t, or Vi of t. Let's let this be R and let's let this be C. And I was basically saying, okay, I've got some kind of an input voltage. Let's go with, draw myself a little plot here. So let's say I had some kind of an input voltage, V in of t, that looked something like this. Oh, wow, okay, wrong tool here. So something that looks just like that. And then, of course, based on the frequency that I'm operating at, this is my 1 over t. This is my frequency, that's t right there. And then I would have some output voltage that I'll draw in red. And it would have some associated phase shift. Let's just say it looked like this. So it's kind of going to peak a little bit earlier. It's going to hit a trough also a little bit earlier. I guess it would have to come from over here, something like that. Man, yeah, I made this pretty ugly. Sorry, guys. Doing my best here. Oh, boy. Yeah, this is pretty bad. It's peaking right there, then. Okay, I tried my best. So this is my V out. This is why I use LT Spice. This is my V in. And so I had some input and some output. Of course, there's some phase shift associated with these, right? Some phase. And then there's some change in magnitude. This is the magnitude here. And this is only at one particular frequency. And so we remember that we could represent the circuit as Vi in the phasor domain, a resistance, a capacitance, or an impedance of, 1 over j omega c. This is R, and then this voltage would just be V out. And the reason why we could abstract away the frequency is because we know that for these linear circuits, the frequency doesn't change. Whatever the frequency of my input voltage is going to be the frequency of my output voltage, which is going to be the same frequency as my current flowing through the capacitor, my current flowing through the resistor, etc. So for these linear networks, the frequency is kind of a constant. Where the things that are changing are the magnitude and the phase of the signal. That's what we talked about with phasors. And we can see that here, like the two signals are at the same frequency. Well, I did my best to draw that was the case, but I didn't do a great job. I tried. So these two signals have the same frequency, but they have a different magnitude and they're out of phase from one another. And so if I were to take this exact same circuit at one frequency, so let's just say that this is at frequency F1, and I were to solve the circuit again at some other frequency, let's say some frequency F2, I would get, for the exact same input, so let's see if I can take the exact same input, roughly. Can I squish it? No, I can't squish it. Dang it. Okay, so I'm just going to have to draw it. So not for the exact same input. It's going to be F2, which is some signal that's even faster than F1. So it's doing something like this. Right? So this is at a much higher frequency. Same circuit. I would get a new magnitude. Something like this. Okay. So let's just assume. Let let me do that. Let me make that even smaller, actually. Just want to get the point across that it's much smaller than this signal, because at some frequency f2, the phase is now different again. I don't have the same phase shift. I have a completely different phase shift, and I have a completely different magnitude. And that, so let me write that here. Frequency 1 was associated with some phase shift, phase 1, and some magnitude. Let's just call it the magnitude of V out 1. This new frequency, F2, is associated with some phase phi 2 and some magnitude V out 2. And so what if I'm interested in 100 frequencies? What if I'm interested in 1,000 frequencies? I don't want to keep doing this. I mean, you can see how tedious this is. I'm not even doing it correctly, and it's taking a long time for me to get to my point, because it's so difficult to solve the circuit for a particular frequency, let alone for 100 frequencies, 1,000 frequencies. What if I wanted to check every frequency from 10 hertz up to 10 megahertz or 10 gigahertz? That's typical in engineering systems. So we cannot sit here and do this sinusoidal steady state analysis for every single frequency. We need something else. And that is what frequency response is. Okay, so I'm going to go ahead and end this video and move on to the next video and talk about this figure. I kind of just drew what I was getting at in the next figure here. But I'll show the figure in the next one, and I'll talk through it again. But basically what frequency response does is it gives us a way to not only analyze frequency 1, to not only analyze frequency 2, but to analyze the entire range of frequencies from DC all the way up to tens, hundreds of gigahertz, all on a single plot that tell us the magnitude and the phase of any given frequency. It doesn't need to be a single frequency, but the entire range of frequencies, okay? And so that is why frequency response is very important and very powerful, okay? So I'm going to go ahead and end this video here, and in the next video, I'm going to go ahead and show my figure and keep explaining frequency response a little bit further before we go ahead and do an example problem or get into how do we obtain the frequency response for a circuit, okay? So I'm going to go ahead and end this right here.